Hello everybody and welcome again to your channel Thermal Engineering Concept and the Principle. In a series of episodes, we are going to introduce the concept of condensation and how to deal with it, whether it was a condensation process over or inside vertical and horizontal tubes. How can we estimate the heat transfer coefficient for condensation of fluids as they pass over the outer surface of tubes? Let us go through the details of this episode. Welcome, my friends and colleagues and followers. The condensation process is one of the important topics present in modern industrial applications in the field of energy and heat transfer. We may find the condensation process in many topics and fields of industry, such as petrochemical factories, refineries, food industry, power plants, air conditioning and refrigeration, and many other topics that is experienced in the field of thermal engineering. The prediction of condensation process and the performance of a heat exchanger is mainly based on the heat transfer coefficient and how accurate it has been predicted. Condensation can occur in different orientations: vertical, horizontal, single, or tube bundle. And in the present episode and the following episodes and videos, I will introduce the condensation process in different categories, whether it was external or internal flow. Thank you for your support and continuous assistance that is afforded by your side to the channel, and let us go directly to the objectives of the present episode. The main objectives of the present episode are we are going to discuss the concept of condensation process on a horizontal tube and how can the condensation can occur on solid surface. Then we will pass through some of the available correlations for prediction of condensation heat transfer coefficient on horizontal tube. A practical case study will be established, discussed, and explore the methods and their utilization, predict the heat transfer coefficient, and finally we will arrive to the closure of the present episode. A concept of condensation process on a horizontal tube In a way, from the physical point of view, similar to that of vertical tube with some principles uh, and some different points, of course. We can't describe it by explaining this process on this illustration. Here we have a horizontal tube where cold water is passing through the uh, tube, and then we have a vapor flows outside the cooling surface. The temperature at the surface is uh, less than the dew point of the flowing vapor, and it's colder than the bulk of the fluid. Then the molecule of the vapor, the substance, will be closer to each other and a coalescence will occur. Then condensation process will take place. Of course, the condensation forms sometimes a thin film on the cooling surface, and due to gravity, this thin film can be washed away, and periodically, regular regular removal of this film from the cooling surface, then the condensation process will continue to uh, proceed until as long as we have a continuous operation or process. Typical available correlations. Of course, we have maybe we may say that we have numerous number of correlations are available in the open literature to predict the condensation process, the condensation heat transfer coefficient and heat transfer rate in the condensation process for horizontal tubes. But I will introduce only three of them. In this table, we have the basis of most of the correlations which are available. In fact, are based on the Nusselt theory in 1916, where he has published equation number one and can be transformed in terms of the condensate tube loading as shown in equation 2a, and this equation was obtained from analytical solution for condensation process on a cold uh, vertical plate. We have 1971 Deer and Leonhardt published a correlation based in its shape on Nusselt equation as shown in 2a, and they replaced the coefficient 0.95 by a value of 0.955 to get the best fitting for their data. And then we have Tarad in 2002, based on experimental data, and he has obtained the best fit for the process where the coefficient was 1.05 instead of 0.955 for Deer and Leonhardt, and it produced a good agreement with the experimental data at that time. Practical case study can be introduced. We have examined the condensation heat transfer where we have a vertical tube in the previous episode. Now we are going to use the same data and information for steam at saturated steam at zero point 0.1 bar absolute with a flow rate of 25 kilogram per hour to be condensed on a carbon steel tube with outside diameter of 22.22 millimeter and a length of 2.5 meter. And we are going to examine the condensation process on that surface where it is oriented in horizontal shape, geometry. And the second part we need to compare the results with the condensation process on a vertical tube. We have the physical properties in table 2. Here we have the last row the critical pressure of steam or water that is 221 bar, and we have also the liquid surface tension Newton per meter. It is 6.86 times 10 to or minus 2. Of course, the saturation temperature of the steam was 45.8, and the other thermal physical properties are shown in this table will be used in the examination of the available correlations presented in this video. A solution for this case study, I will start with the Nusselt correlation as shown in table 1, and we will start with the condensate tube loading, which is m dot f divided by L tube. It is equal to 0.278 times 10 to the power minus 2 kilogram per meter second. Using this value in the form of equation 2a of table 1, we may substitute the values of the condensate tube loading and the thermal properties of steam and liquid. Then we will get a heat transfer coefficient which is equal to 7,218.04 watt per meter square Kelvin. Then we will examine Deer and Lianhar's correlation as shown in table 2. In table 1, again, we will substitute the values of the thermal properties with using the condensate tube loading and with the factor 0.955. Then the heat transfer coefficient of the condensation process will result in a value corresponds to 7,256 watt per meter square Kelvin. And then if we go to Tarrant's correlation, similarly as shown in equation number 4, then we will get a heat transfer coefficient equal to 7,977.8 watt per meter square. Of course, as a summary and comparison with the vertical results which can be deduced from the previous episode, it's clear that the horizontal tube produces higher heat transfer coefficient than the vertical tube, and this can be attributed to the fact that the horizontal orientation produces a more uniform condensate film, resulting in steadier heat transfer, and due to gravity factor, this film can be removed from the cooling surface, allowing the vapor to be in contact with the cooling surface directly rather than the existence of the uh, condensate film. And of course, this will drains the uh, condensate smoothly and improves the heat transfer rate when compared with the vertical tube. We have other correlations can be found in a list of references will be um, found in the uh, description box of this video. Dear friends, now we have arrived to the final section of our video and lecture for this episode. We passed through the description of the concept for condensation process on a horizontal tube. Then we mentioned some correlations that are available in the open literature to predict the condensation process from vapor at a horizontal single tube. And then finally, we took a practical case for the condensation process and we compared it with that of the vertical tube, which we have mentioned in previous episode. There are some valuable resources can be found in a PDF form with a link presented uh, in the description box. If you have found this information are useful to you, please subscribe and share it with others. And we will meet again in other videos for the prediction of condensation heat transfer coefficient. Bye bye.